Okay, so hi everyone. Welcome back to our new One Word ABC seminar. It's my pleasure to have here today Alex Aushev, who will be talking about sample efficient inference for simulator, complex noise model, and time series. Thank you, Alex. The floor is yours.
Okay, thanks. Yeah, so today's talk will be about inference with simulators that are computationally heavy. And we will cover two topics, which involves complex noise models and time series. So just like a quick recap of the likelihood-free inference. So I'm mainly using this slide to introduce the notation. I'm sure that everyone knows the premise. So we have simulated parameters. We generate data sets with some simulator, and we summarize these data sets. And essentially, we want to know which simulator parameters produced the data sets that are observed. And the way, for instance, how it is done in ABC is through some discrepancy metric, which can be, for instance, Euclidean distance. And the idea is that if the simulators generate synthetic observations that are very similar to some distance measure to the observed data set, then it is very likely that these are the parameters that they produced the observed data set. And we see the formula below, where we essentially have the prior multiplied by this integral, which essentially replaces the likelihood. Kappa epsilon here is some kind of a smoothing kernel. P of s theta given theta is the simulator that we sample. And the role of this epsilon is essentially a bandwidth of the kernel, and it acts as some kind of a acceptance rejection threshold. Yeah. So since we will be talking about computationally intensive simulators, I need to spend a few minutes here. So computationally intensive simulators do not necessarily require 1 hour, 1 day to do one single simulation. So it's usually a trade-off between how much simulations you want to make and what's the time of one simulation. So even if the simulator takes 100 seconds, which is very small time to generate synthetic data sets, it already takes a huge toll on the inference time. Let's say when we have 10,000 simulations. So we would need something like 11 days and 13 hours to do inference, which is, of course, quite unfeasible. So what we want to do essentially is we want to reduce the amount of simulations our inference algorithm requires to produce some reasonable solution. Yeah, so there are several ways to tackle the simulators that take a lot of time to compute. So one way is to, let's say, increase the processing power, or let's say run simulations in parallel. So a lot of the inference algorithms do that, and we will not cover this in this presentation. Another way is to, of course, reduce the accuracy of the solution. So, for instance, by decreasing the tolerance threshold that we were talking in the first slide. Yeah, and the third way is to make some kind of like a simplifying assumptions. Of course, these assumptions need to be reasonable, and essentially these are like modeling assumptions. For instance, we may assume that the simulator noise is, let's say, Gaussian. So that's already makes the inference a little bit easier. So as I've already mentioned, this talk is consists from two parts. In the first part, I will talk about the complex noise, and in the second part, I will be talking about the simulators in time series. And the overarching topic of this presentation is computationally intensive simulators. So we will talk about these two topics which are important for them. Yeah, so starting with the first one. So this part of the talk is roughly based on our joint paper with Henry Pessonen, Markus Heinonen, Jukka Karander, and Samuel Kaski. And it's called likelihood free inference with deep Gaussian process. So that's already a spoiler in the title. So so one way of tackling the simulations that take a lot of time is to use active learning. And by doing this, we essentially can reduce the number of simulations. So we can represent the discrepancy measure as some kind of a function that depends on theta. And we can assume a Gaussian process prior over this discrepancy function. And by doing this, we essentially can use GP uncertainty in order to choose where to run the simulator next in some kind of like intelligent way. So, for instance, we will try to minimize the acquisition function, which is A. On the figure, it is shaded in the green. So the arrow shows where would we sample our simulator next. We use this simulation as a new point for a Gaussian process. We get a better fit. And once we exhaust all the simulation budget, we can extract the posterior. So recall the formula from the first slides, and we use the surrogate in a very similar way to get the posterior. So we need to choose some kind of epsilon, and once we do this, we essentially weight the prior, and we get the posterior. Yeah, so when we use Gaussian process, we make a lot of implicit assumptions about the discrepancy values. So the figure shows the distribution of the discrepancy at different locations theta. And we see here a multimodal noise, at least on the edges of this function. And if we try to fit this with a standard Gaussian process, we would get the figure in the middle, where the solid black line is the mean function of the Gaussian process, and the gray area is the 95% confidence interval. And we get this bad fit because the Gaussian process assumes that the noise is Gaussian, and it tries to fit both modes essentially with a Gaussian, which results in this bad fit. So what we would like to have here is we would like to fit the discrepancy better, and we want to separate the modes. So on the right, you see a deep Gaussian process fit, where the shade of blue represents the density of the deep Gaussian process predictive samples. So a part of the solution is to use like a more flexible surrogate, for instance, a deep Gaussian process. So one of its benefits is that it is much more flexible, but we lose a lot of very nice properties of the Gaussian process, and it is in general much more difficult to work with deep Gaussian process. So we need to use somehow the deep Gaussian process fit in the acquisition functions and in the posterior extraction procedure. And what we can do is we can essentially use the predictive samples of the deep Gaussian process at a certain location. So the figure shows the distribution of the discrepancy for a certain location theta. So, and the y-axis is the density, essentially. Where the green area is the true density, the black-red line is the Gaussian fit. And what we propose is to use the quantile-based filtering idea, where we essentially filter the predictive samples of the deep Gaussian process according to some quantile function q, where it takes the percentile as an input. For instance, on the figure we filter, I believe, 70%. So the remaining part consists of like 30% of all the predictive samples. And once we apply this quantile modification, we essentially can approximate the remaining part with the Gaussian, And by doing so, we retain a lot of the nice properties of the Gaussian process. We don't spend much computational power on how to calculate things exactly, and essentially it produces a much tighter fit to the simulator noise, which improves the accuracy of our likelihood-free inference surrogate modeling approach. And this slide shows the some of the experimental results. So we plot the deep Gaussian process architecture, with which consists of the two Gaussian processes, and we compare it against vanilla Gaussian process. So the y-axis shows the Wasserstein distance between the posteriors produced by the surrogates versus the posterior, which was generated with the ABC with rejection sampling, with a much higher computational budget. And on the left, we see that we see the test case for the problem where the simulator noise is roughly Gaussian, so at least it is unimodal. And once we increase the budget, we can see clear signs of overfitting in the deep Gaussian process, while the GP fit remains roughly the same, with a much reduced variance. So this whiskers essentially show us the variance, and the horizontal lines, it shows the mean. Yeah. So if we use something like some test case with the multimodal simulator noise, we will get a much larger gap between the deep Gaussian process and Gaussian process. So the takeaway messages for this part is that when we use surrogate modeling approaches to likelihood-free inference, we make implicit assumptions about the simulator. So for standard Gaussian process, we assume that simulator noise has the same distribution family for all simulator parameters. So at all simulator parameter locations, we are assuming that simulator data generation mechanism is stationary, and we're assuming that the simulator noise is approximately Gaussian. So when we know all this stuff for the simulator, it is fine to use Gaussian process, and we would get a good results with it. If we don't have a lot of prior information, prior knowledge that we can incorporate it in our inference algorithm, we can use deep Gaussian process, which make fewer restrictive assumptions, but it comes at the cost that they require more data, and there is a risk of overfitting in case the simulator is quite simple and doesn't really need deep Gaussian process. And some of the alternative solutions to the problem of complex simulated noise is to use some semi-parametric models. For instance, neural density estimators, or if the setting allows it, we can use some amortized inference approaches if we know that we will be using the same simulator with multiple observations. And another possibility is to change the summary statistics, so the resulting space satisfies the assumptions of the surrogate. Yeah. So that's the first part of the talk. The second part is based on on our joint work with Thong Tran, Henry Pessonen, Andrew House, and Samuel Kuski. Yeah. So now we are moving on from the complex noise to the time series, so which represents another problem for computationally intensive simulators. So in the traditional way, we have simulated parameters theta as a latent random variable, and we're giving the observed data set, and g theta is the simulator. So in the setting that we will consider in the second part, thetas change according to some unknown latent stochastic process. We have multiple observations at different time steps, x1, x2, etc., and we have the constant simulator. Constant meaning that it remains the same throughout the whole time series, and which is essentially can be represented as a state space model. So the motivation for considering this setting comes from the cognitive modeling. So in cognitive modeling, we often have some model of the human behavior, but we are not sure how it evolves in time. So for instance, on the left, we see this figure of the screen, and it represents a gaze-based selection task. So one of the cognitive models describes how humans select something with their gaze, which is helpful in the medical settings, in some VR or AR applications. And the task essentially is to find the cross, the red cross on the screen with the gaze. So the human starts at the center, and in the several movements with their eyes, which is represented with the orange arrows, it finds the target. So the model here is some kind of a reinforcement learning agent, and we record the time in which the human participant was able to find the target. So the problem with these types of tasks is that if it is very rarely when you give the human participant only one design trial. So usually you want to give them several of them, let's say 10, but the problem is that the the participant adapts to the task, they become much better at it. So the parameters of the models will change. And what we want to do is we want to track essentially how these parameters change, and we want to use it to improve the inference quality. Yeah, so the current methods fall into three major categories. So state space inference, state space learning, and likelihood free inference methods for state space models. So the difference between them is how they treat the observation model. So quite often in this state space inference algorithms, the observation model, its likelihood is given, and the H, which is a transition dynamics, is known. So state space learning methods, they learn the observation model, and they also learn the dynamics. So they're essentially given the time series, and they are able to find some kind of a state representation, which is learned. So in likelihood free inference, G, of course, is a simulator. So the states are not learned. So they have the advantage of being interpretable. And quite often the transition dynamics is also known. So the question is, like, what if the H is unknown and the simulator is computationally intensive? Okay, so I see that I have some rendering issues with the. Okay, so you see these squares, they should be essentially deltas. So these are the discrepancies which correspond to a certain time steps. So what we want to have is that we want to extract posteriors for each single time step, for each observed data x, and we do this by using a very similar idea that we've seen previously, to use a surrogate for the discrepancy function. And here we're proposing to use a multi-objective surrogate. For instance, linear model of coregionalization, which is essentially it represents the objectives as a linear combination of Gaussian process, where the A is the coefficient of the linear combination, and U is a latent Gaussian process. And we have like Q, Gaussian process. And essentially, the idea of such multi-objective surrogate is that it shares the same parameters between the time series, and it provides some kind of a regularization, which improves the fit of the surrogate. Yeah, so I also need to spend some time to like explain the different sets which essentially transfer the information between different parts of this scheme. So S are the simulated parameters. So we generate synthetic observations with them, and T, we pair them with the discrepancies, and we use it to train the multi-objective surrogate. And then we extract the posterior, similarly as we've seen before. And this P is a set of the state posteriors at each time step. So it essentially consists of the samples from these posteriors. And so one part of the solution is to use a multi-objective surrogate in the setting. And another part is, well, essentially is to learn the transition dynamics, which is denoted as H theta with a wave above. And for instance, we can use a Bayesian neural network as such a transition dynamics model, which is trained in a autoregressive fashion using the samples from the likelihood-free inference posteriors. So we pair the consecutive we pair the samples from the consecutive posteriors, we pair them randomly, and we use them to train the transition dynamics model. So we have plenty of very, very, very noisy data, and we use it to train the transition dynamics model. So that's essentially the training set D. And then we can use this transition dynamics model to propose the simulations for future time steps. And yeah, so that's the general idea of the approach, is that first to use the multi-objective surrogate for the discrepancies, and then to learn the transition dynamics in this way. So the results are the following. So on the so these figures, they measure the root mean square error between the estimated state points versus the ground truth state points. And we essentially evaluate a whole bunch of different methods. So we use LMC as the surrogate for the discrepancies, and we experimented with the Bayesian neural networks as transition dynamics model. We also tried to use a Bayesian linear regression as a transition dynamics model. We also tried to not use the transition dynamics model and use a multi-objective acquisition function, which is a Q expected hypervolume improvement. We used classic Bayesian optimization for likelihood-free inference, so without any knowledge of the transition dynamics, and we used three different types of the sequential neural estimators for the posterior, for the likelihood, and for the ratio. And yes, so we see that in the case where the dynamics was completely unknown, in a preference learning task where essentially the human user needed to solve a data analysis task where they first try to explore the data and they gradually move to finding a very good machine learning model which would be able to separate the data very well, and the transition dynamics essentially simulated this path. So, and the transition dynamics model tried to suggest some new configurations for the embedding algorithm, which would suit the task that the human is trying to perform. So that's a very lengthy explanation. So the bottom line here is that it's a test case where the transition dynamics is unknown. And the second case study is where the transition dynamics was roughly logarithmic, and it was the Gaussian-based selection task that I've introduced earlier. And so we see that for the unknown dynamics, where the dynamics is very unexpected, like where it doesn't follow some known functional form, there is a clear benefit of using a transition dynamics model. And for the logarithmic part, we see that the Q expected hypervolume improvement, the green box essentially performs better, slightly better than the transition dynamics model proposals. So that's the most benefit comes from using the transition dynamics model when we don't know the functional form of the dynamics. So that's the bottom line of these experiments. So the takeaway messages from this second last part is that this multi-objective likelihood for inference approach can be applied when the simulator is static and when we have no information about the transition dynamics. So in such scenarios, we get the most benefit from learning the transition dynamics. And the sample efficiency of this approach comes from leveraging information between states through the multi-objective surrogate, and also from using predictive samples from the transition dynamics as to generate simulation proposals. So the alternative solutions to these problems in time series is to use amortized inference. So essentially, so these are the types of the algorithms that are trained on a wide range of possible observations. And if we know that we're going to have a lot of time series, it is quite often very beneficial to spend this time learning some amortized inference approach, amortized inference model. And the second way to tackle the problem is to try to integrate the transition dynamics in the simulator and treat it as a classic likelihood for inference problem, which is often not possible. For instance, that's the case for a lot of the cognitive models. Yeah, and here's just the summary of the talk. So these are the main takeaway messages from the first and the second parts. So yeah, you can get more information through the from the papers below. The links are provided, and that wraps up my presentation. Thank you very much.